Okay, so let's look at some sets here. So let's see how this all works out. So in this example, we have this subset of R3 is linearly independent, right here. So S is literally independent. So let's look at some supersets, okay? Let's look at this one. We'll say the set of 1, 0, 0. And then we'll consider the set that set. Okay, so now both of these are supersets of set S. Now, this one is dependent. Why? Because we can see that this is in the span of S. Okay? So S is everything on the axis, the x-axis, right? So it's the x-axis. And so this is just another vector that's on the x-axis. So there's a lot of reasons why we could see that this is dependent. This is independent. Okay? Adding this, this didn't change the span, right? So adding this didn't change the span of S. But if we add this, this is an independent set because now we're adding the y variable. So this represents, the span of this represents the xy plane, okay? So it did increase the span, okay? So let's go another step. Let's change this. So let's say S is now this. So now this is independent, right? S is independent. So now we're talking about the span of S, which is the xy plane. So now let's consider these two sets. And we'll add this one. And on this one we'll add another one. Okay, now, if we look at the same thing, look at these two supersets, okay? This one is dependent, right? You can see that this doesn't change the span of S. You can also see that you can get a linear combination. This one is equal to a linear combination of these two. So this is a dependent set. But this one is independent. There's no way you can get a linear combination of these two to get this one, because there's just no z coordinate here, okay, or z element. Okay, these are independent, but also you can see that we're going to a different span, right? So by adding this vector, we're moving from the xy plane to the XYZ, right? We're looking at all of R3. Okay, so as we did before, the additional member of the dependent superset comes from S, comes from the span of S. Okay, so the additional member of the dependent superset comes from the span of S, right? While the added member to the independent superset comes from outside that span. Okay? So again, we're seeing the same thing that we've been talking about. So let's do one more. And so let's expand this and add this vector to S. And so now this represents all of R3. All of it. Okay? So, well, let me be more precise. This doesn't represent R3. The span of S represents all of R3. That's what I should say. Now, we can get a linearly dependent superset, right? So we can get a superset by just adding another vector. And so we can add this vector here and so we can get a dependent set, right? So if we add another vector, we can see that this is going to be a linear combination of these three, right? So the question is, can I add another vector to this set to make it linearly independent? And the answer is no. There is no way to get a superset of linearly independent vectors. Okay, and because I can get all of x, y, z, right? So I can get any vector in R3, x, y, z, as a linear combination of the vectors in S. Like so. Where C1 equals X, C2 equals Y, and C3 equals Z. Another way to see it is that we cannot add any vectors from outside the span of S because that span is R3. Okay, so that's another way of looking at it. Either way is fine. And that's it. Have a great day.